Hello guys, welcome back to my YouTube channel. My name is Trishaliji and I'm studying in Sri Venkateswara College of Engineering, and I'm here today to explain something about Unix systems, that is aimed to process communication, its introduction, and pipes and FIFOs. Communication between processes. So isn't it very necessary for one process and another process communicate with each other so that it can have a faster output? The processes live in different worlds or different memory address spaces due to the virtual memory. So communication between the processes is very important. That is maybe killing a process from a shell command or sending data between the processes. So as we can see, for example, process A is address space and process B is address space. So communication between them. Now inter-process communication, that is the IPC. Cooperating processes or threads need inter-process communication, that is for data transfer, for sharing of data, for event notification, for resource sharing, and from process control. So the processes may be running on one or more computers connected by a network. So the method of IPC used may vary based on the bandwidth, latency of the communication between the threads, and the type of data being communicated. So IPC may also be referred as your inter-application communication. IPC mechanisms, or basically you can tell IPC types. So IPC mechanisms are divided into signals, pipes. In pipes we have unnamed pipes and named pipes of FIFOs, message queues, shared memory, map files, semaphores, RPCs, and your sockets. Now IPC, unnamed pipes, a byte stream among processes. Bytes written by a process is readable by another process in the other end. So that is what an unnamed pipe can do. So where we can use all this is in a shell passing the output of one program to another program. So there are two programs running continuously. The second program depends on the first program's output. So for example, cat, file 1, file 2, you're sorting it, etc. Now what are the limitations of these? Processes need to be relatives, that is, it should be parent, child, siblings. They cannot be used for broadcasting. Data in pipe is in the byte stream and has no structure. There is no way to distinguish between several readers or writers. Implementation. Internal kernel buffers, socket buffers, or stream interface. Now, pipes. A pipe is a data structure in the kernel. The data is stored in the kernel buffers temporarily, no random access on pipes. Okay, so a pipe can be created using a pipe system call, that is int pipe int star fd. So fd is an array of size 2. Now two file descriptions are returned, fd of 0, that is open for reading, or fd of 1, that is open for writing. So some systems implement bidirectional pipes, both ends are readable or writable. So typical buffer size is 512 bytes, that is the minimum limit defined by the POSIX, and it reads and writes may be blocked by the buffer. Now, pipes can be used for, or pipe is created by a process. This process calls fork. Okay, the fork and braces, parenthesis, is the function name. Okay, so file descriptors are inherited by a child. So a pipe is shared with the child. So a pipe used in communication between the parent and the child. So a pipe provides one-way flow of data. It is unidirectional. Example, output of, as you can see, who, sort, and LPR. Output of who is input to sort. Output of sort is input to LPR. So this is another example. You are declaring a track to keep the number of bytes, and you are holding FDS of both the ends of the pipe. You are declaring the PID of the child process and a buffer to hold the text for reading or writing. Okay, then you create your pipe. Then you fork, call the fork function. You are checking if it is equal to, if it is less than 0 first, fork it. If it is less than 0, if it is greater than 0, parent processes, it closes the read end and it writes to it. Then you read from the pipe and then echo to the screen. Now after the fork call, as you can see in the picture, standard in, standard out, standard out, 3 types. That is your descriptor table for the parent, FD1, 2, 3, 4, etc. Here file DES of 2 gets 3 and 4 as a result of pipe call. So when the pipe call function is called, 3 and 4, FD of 3 and 4 gets the is the memory space being occupied in 3 and 4. Next, for the descriptor table, for the child also 3 and 4. See, from 3 to 3 and then from 4 to 4. Now, after the close calls, then there is a close function. You close the FD of 3 for the parent, then FD of 4 will be closed for the descriptor child. Okay, so this pipe allows parent to send the data to the child. If a two-way communication is needed, then the parent needs to create 2 pipes before fork and then use a second pipe as the channel. Systems with bidirectional pipes can do it in a single pipe also. So the other end does not get the end of the file if at least one process is keeping one end open. Always close the end that the process will not be, where the process will not be used. Next, unnamed pipes in the shell are used with redirection. For example, as you can see there. Shell setups of standard out of the child to pipe write standard in of next one as a pipe read. So you write in the child and then you pass your output to the next thing. So that is a sample example. So there we have int fd2 to hold the fds of both ends of the pipe. Then you're creating the pipe. Then you're calling the parent process using the fork. But we are not going to use that. We wait for both the child and the parent, and then you make the pipe read the child. Now you're not using the right end. You can see you're closing there. Then the DOP2, you're redirecting the standard in to read end, and the close function, then it is duplicated and it is closed and it runs in the binary, as I told you, binary bytes. Then you're not using the read end, then you're redirecting it to write and then it's duplicated, again it closes otherwise. Now IPC, that is your named pipes or FIFOs. So pipes are restricted to processes of the same family, relies on the file descriptor inheritance. So FIFOs are pipes named as a path on the file system. They can be accessed by any process that knows the name. Pipes are temporary. They disappear when last processes close. FIFOs or named pipes are special files that persist even after all the processes have closed them. A FIFO has a name and permissions just like the ordinary file and appears in the directory listing. So any process with the appropriate permission can access a FIFO. A user creates a FIFO by executing the make FIFO command and a command shell by calling the make mkFIFO system call within the program. As you can see, FIFO creation in the cell. Make FIFO name, then your mode name and the namespace. Make sure you remove your pipes after the use. So that is a small program. Next, how do you use named pipes? First, you create your pipes. Make FIFO pipe 1, 2 or 3. Then attach your data source to your pipes using the and symbols. Then read the pipes from using the reader process and then delete your pipes. Now IPC FIFO mkFIFO system call. So this is a function mkFIFO system call. As you can see the syntax given, int mkFIFO constant char path mode t mode. So the mkFIFO function creates a new FIFO special file corresponding to the path name specified in the path parameter. The mode parameter specifies the permissions for the newly created FIFO. So if successful, the function returns 0, otherwise it returns -1 and sets to error. Okay, that's it for today guys. Thank you so much.